You know how this is going to go. We started with position back in late August. Then we went to displacement, velocity, and acceleration. Displacement, velocity, and acceleration. That was all linear. Now we're going to look at those same ideas in a rotational angular context. We might not get to A in this video. I'm not quite sure how it's going to go, but we might end up reserving A for the next video. But we're at least going to hit displacement and velocity in a rotational context here in this video. So, you remember linear displacement, right? There it is in all its glory, right? If our bug starts at x equals 0.5 and walks to x sub f is 3.0, delta x is the displacement, and it's equal to the final position minus the initial position. Now, this is all one-dimensional stuff. And circular motion like this is analogous to a one-dimensional situation. We don't have to worry about x and y over here. Okay, just x. It's all going to be analogous to a one-dimensional situation. You got your positive direction counterclockwise, your negative direction clockwise. Okay, so we don't have to worry about putting vector signs over these and all that kind of stuff. Okay, delta x is xf minus xi. So in this case, the displacement of the bug is 3.0 meters minus 0.50 meters. And the displacement of the bug is 2.5 meters, right? And the positive sign that's not explicit here tells you that the bug moved in what we have defined as the positive direction. Had the bug started at 3 and gone until 0.5, then the displacement will be negative 2.5 because the bug would have gone in what we define to be the negative direction. Translate that over here. Let's say that the bug's initial position is at 0.50 radians, and that the bug's final position, final the final angular position is 3.0 radians. Now, I didn't mean to make it 0.5 and 3 on both, but maybe it was just subconscious. I don't know. Okay. So in this case, you can see what's going to happen, right? The angular displacement is delta theta, which is, not surprisingly, theta f minus theta I, which in this case is going to be 2.5 radians. So the bug traveled 2.5 radians. Okay. Now, as he did so, he went through this arc length S. And by the way, arc length has units of meters just like any other length. Okay. But this angular change here of 2.5 radians says nothing about how big this circle is or how far the bug actually walked. If this is a very tiny circle, the bug walked a small distance. If this is a very large circle, the bug walked a large distance. But we don't care about how large S is. The angular displacement only tells you the change in angle between the initial point and the final point. And that change in angle is exactly, let me actually see if I can indicate this with yellow perhaps, right? This 2.5 radians here is the size of this angle right there. That angle there is delta theta. Between them, the size of that angle, that yellow angle there, is 2.5 radians, and that is the angular displacement of Mr. Red Bug. Okay. So that is angular displacement. And it can be positive or negative. Just like linear displacement is positive in this example, but the bug could have gone that way. Right? Nobody's stopping the bug from going that way. He just chose freely to move to the right, what we call positive. So we called his displacement positive. This red bug over here, same red bug, just a different time. Here he could have gone the other way. He could have gone around the circle this way. Okay? In that case, his displacement would have been negative. So displacement can be positive or negative in both cases. Had the bug moved in a clockwise sense, then his angular displacement would have been negative, because he would have started off at a larger. I mean, he would have ended up at a small angle than he started with. Okay, so hope you see the analogy. The analogy doesn't stop. In fact, the analogy actually never stops. It keeps going. It keeps giving. So we had linear displacement in delta x. We also had linear average velocity. Remember that? Delta x over delta t, right? We defined it in terms of the displacement. Okay. Well, if we put in theta for x, what do we put in for v? We put in, I should say linear average velocity. We also have linear, we have rotational average velocity. Or either the average rotational. Let me just write it this way. Getting lost in the thicket here. So, what is the equivalent of this is what I'm asking, of V average, right? Because the bug might have gone from x1, x sub I to x sub f very quickly. We didn't know how, I never talked about how long it took to get there, right? So the bug might be going, if you went very quickly, this would be a large number. If you went very slowly, that'd be a small number. Same thing here. The bug might have changed angular position very slowly or very quickly. Instead of V average, we have something called omega. That's just like a little W with a flag on it. The Greek letter omega is equal to delta theta over delta t. And this is known as a rotational velocity or angular velocity. Actually, this is average angular velocity in the same way that this is average linear velocity. Okay, so average linear velocity, V average, delta x over delta t, been there, done that. A new thing is happening. We now have average angular velocity, which we indicate with the letter omega. Okay, and it is the change in angular position, that is the angular displacement divided by time. How quickly did the bug get there? If he went very quickly, this would be a large number. The average angular velocity would be large. If the bug went slowly, took his time, chilled, then his average angular velocity would be small. Note the units. The units here are radians per second. Right, units over here are meters per second. Right? Units here are radians per second. Okay? Angular velocity. Now that is average. There is also have instantaneous omega, just like over here we also have instantaneous velocity. Right? And there's a distinction between the two. Instantaneous velocity in linear land is just the velocity at any given instant. Okay? Same thing over here. We have instantaneous velocity. In other words, maybe the angular velocity is changing. Just like over here, maybe the linear velocity is changing. Maybe he's going from 0.5 to 3 and going faster and faster. So his velocity is actually changing. He's got an average velocity for the whole trip, right, given by this. But at any given point, we can take a snapshot, sort of a freeze frame, and ask what is the bug's velocity at that point in time. That's what we just call a plain old v, and like in all of our equations of motion, right? Plain old v. Same thing here. Okay. Maybe the bug is going to start off real slow and kind of relax and chill. Maybe he'll stop for a while. Maybe he'll back up. And then maybe at the end he'll sprint, boom, to this point. We have the average velocity over the whole trip, the total delta theta over time. But also at any given point during that trip, we can take a snapshot of the bug and ask ourselves, what is his angular velocity at that point in time? So, in the same way that we had average and instantaneous, we have the same thing. And I need to put, this is important, I think I'll make it a brighter color so it'll stand out. I've meant to put average right here. Okay. Same way there's an average over here. Okay. All right, now before we end this video, I need to talk about one last thing. I've got enough room to put it right down here. Hope this analogy is helpful and clear. Okay. Rotational stuff is difficult. It takes a little bit of wrapping your head around, and I completely get that. But the nice thing about it is that you always will have an analogy to something we've already done. And the analogy is beautiful all the way through. Okay? So you always have that to sort of lean on, okay, which is nice. The last thing I need to do is introduce to you something, a term called the period. Okay? And this really has to do with angular velocity over here. Okay? But I'm going to put it down in the bottom down here, the period. Okay, the period is a simple idea. It's the time required for one. How do I have it written here? Required for one revolution. It's a time. It's a period of time required for a single revolution. Now, typically we talk about period when we're talking about something that happens over and over again, like a bicycle wheel zipping around in circles, or a game show wheel rotating. Okay, it's any motion that repeats itself has a period. It can even be wave motion. Okay, any motion that is cyclic, that repeats itself over and over again, has a period. Okay, has a period. Now let me see how I did this here. Now we've got this definition here. Omega is equal to, let's say we have a wheel or a bug that's moving around at constant velocity, constant angular velocity, just chilling, going in circles and circles. So we got our bug here just walking in circles all day long. Okay, so his average velocity is equal to his instantaneous velocity. So it's delta theta over delta t. Okay, so in one period, okay, how far does he go? If we set the time to one period, and the period has a symbol t, okay, I should have said that. T, period has a symbol t. Okay, I think we use t in this book. Yes, t. Sometimes it's p. T and the units are just going to be seconds. So if we allow the bug to travel for one period, how many radians has he gone through? If he goes one period, means he's gone around one whole time, 360 degrees, which is 2 pi radians. Okay. So we can rearrange this for the period, and the period is equal to 2 pi over omega. Okay, that is the period. That's the connection between the period and the angular velocity. Okay. Just wanted to stick that here at the end because it's important. It'll come up again. But you can see why there should be a connection between the period and the angular velocity. The higher the angular velocity is, the shorter the period is, right? So if omega is big, if the bug's really trucking, zipping around real fast, omega is really big because he's moving very quickly. The angle is changing very quickly, which means that t is small. It takes him very little time to go around once. Also, if omega is super big, if he's going really, super small, he's going super slow, right? It's a speed. So if he's just chilling and going real slow around, the period's going to be large. So if omega is small, the period will be large. That's the connection between the two. Next up, rotational acceleration and more on the analogy. See you then.